This time, I'm going to talk about UMAP dimensionality reduction in Python. UMAP is an acronym for Uniform, Manifold, Approximation, and Projection, and it is a dimensionality reduction technique. There are many dimensionality reduction techniques. Here, I listed several popular dimensionality reduction techniques like LLE, t-SNE, UMAP, MDS, PCA, and UMAP. In my YouTube channel, I have several videos explaining LLE, t-SNE, and PCA. If you haven't watched those videos yet, you are welcome to watch them too. UMAP, as I mentioned, is a dimensionality reduction technique. It assumes that available data samples are evenly or uniformly distributed across a topological space or manifold, which can be approximated from these finite data samples and mapped or projected to a lower dimensional space. Now you know UMAP is the acronym for Uniform, Manifold, Approximation, and Projection. Let's go through those words one by one. Projection is a mapping of an object from high dimensional to low dimensional space. When we talk about approximation, that means the algorithm assumes that we only have a finite set of data samples, not the entire set that makes up the manifold. Hence, we need to approximate the manifold based on the data available. A manifold is a topological space that locally resembles Euclidean space near each point. The uniformity assumption tells us that our data samples are uniformly distributed across the manifold. I will talk about this uniformity assumption in more detail later. UMAP is a dimensionality reduction technique very similar to t-SNE. Now, let's take a look how t-SNE works, and then we are going to compare UMAP and t-SNE. t-SNE is based around all versus all table of pairwise cell-to-cell distances. Now, let's take a look at this example. Please keep in mind, when we are doing the real data analysis with real data, we don't have all those labels. That means we don't have all those red color or blue color. We label them here because we want to validate our model later. So with t-SNE, we are going to calculate cell-to-cell distances for all of them. So for this red dots, we have those distance, and for the blue dots, we have those distances. Of course, we are going to calculate all the distances also among red dots and blue dots, and also here red dots versus blue dots. And you can see in this cluster we have smaller distances, and this cluster and this cluster we have larger distances. Of course, among all those blue dots, we also have relative smaller distances. There is a very important concept in t-SNE, perplexity. Perplexity is the expected number of neighbors within a cluster. For example, if we say perplexity equals to 2, that means for this data point, we want 2 neighborhoods. So including itself, it will be 3. And perplexity equal to 2 in this graph will say, okay, those 3 is a group because they are close to each other. And for those 3 blue dots, they are one group because they are close to each other. Perplexity in t-SNE is critical. For example, if we have 5 data points here, 5 data points here, visually we can see there are 2 groups here. If we choose perplexity equal to 4, and then we are going to get the correct result. And you can see we will have this red group and blue group. But if we choose perplexity equal to 2, you will get too many small groups. And if you choose perplexity equal to 5, you can see the different group, they will overlap. Just like I mentioned, perplexity is very critical in t-SNE. Also in this example, original data points are located like this, and if we choose perplexity equal to 2, we will have so many small groups. And if we choose perplexity 30, and then they clustered together nicely. If we choose perplexity equal to 100, you can see all the data points, they kind of mix together. In t-SNE, cluster sizes are meaningless. Let's take a look at these original data points. We have this larger cluster and this smaller cluster. And if we choose perplexity equal to 2, you can see we don't get correct clusters. And if we choose perplexity equal to 5, we can see those clusters separated but with similar size. And if you choose perplexity equal to 50, they separated nicely but with the same size. That means cluster sizes are meaningless in t-SNE. And also, the distances between clusters can't be trusted in t-SNE. T-SNE only gives reliable information on the closest neighbors. Large distance information is almost irrelevant. In this original data points, you can see we have 3 groups here, and the blue and orange, they are kind of close to each other. If we choose perplexity equal to 2, we can't really separate them. And if you choose perplexity equal to 5, they are separated with almost same distances with each other. If we choose perplexity equal to 30, you can see we can separate them nicely, but you can't tell the original group is closer to this blue group in this result. But from the original chart, you can see the distance between orange and green is farther away, and you cannot tell from this result after you run t-SNE. Okay, about t-SNE, it is unlike PCA. It is a stochastic algorithm, so it will never produce the same output unless you use a seed to log the random estimators. Of course, I'm using Python for this t-SNE algorithm. We use this seed function. And the cost function never reaches the minima, and it is not an indicator how good the graph looks. The cost function in t-SNE minimizes the distance between similar points. The distance within a group are slightly meaningful, but not between groups. I just showed that in previous slide. Lastly, to add more samples, you need to rerun the algorithm from start. So we realize there are several questions or problems with t-SNE. Now we can use UMAP to address them. Instead of the single perplexity value in t-SNE, UMAP defines first nearest neighbors. That is the number of expected nearest neighbors. Basically the same concept and perplexity. But besides that, we have minimum distance. This is how tightly UMAP packs points which are close together. Nearest neighbors will affect the influence given to global versus local information. Mean dist will affect how compactly packed the local parts of the plot are. So, comparing with t-SNE, we have this minimum distance in UMAP. Now, we assume a uniform distribution of points across the manifold, suggesting that space between them is stretching or shrinking according to where the data appears to be sparser or denser. Like I just mentioned, in t-SNE, we have a unique perplexity for our model. But in UMAP, based on the data point where it is located, we can have this distance metric sometimes larger, sometimes smaller. So it essentially means that the distance metric is not universal across the whole space, and instead it varies between different regions. Also, UMAP skip a normalization step in the calculation of high dimensional distances, which speeds it up. In the 2D projection, UMAP uses a more efficient method to shuffle the cells into their final position, like this. In summary, UMAP is a nonlinear graph-based method of dimensionality reduction. It is very efficient. There is a problem with nonlinear dimension reduction methods because they tend to be computationally intensive. A common practice to reduce this burden is to first apply PCA to data and perform dimensional reduction on data projected to leading principal components. So UMAP can be run from the top principal components. Please keep in mind, this method is not unique for UMAP. You can also first apply PCA to your data and then use t-SNE on data projected to leading principal components. And further, UMAP can use any distance matrix. UMAP can integrate between different data types, like text, numbers, and classes. UMAP is no longer completely stochastic as t-SNE. UMAP defines both local and global distances, and it can be applied to new data points. Now, I'm in Google Colab. This is the model we are going to perform dimensionality reduction with UMAP. I will upload this source code to my GitHub so you can download it and try it by yourself. In this video, I'm going to use digit numbers for our process. All those digits, they have 8 times 8 pixels. So there are 64 pixels per image. That means at the beginning, we have 64 dimensions for our data. And then I'm going to apply UMAP to our data. There are many parameters for UMAP. I wrote the description after each parameters. So after you download the source code, you can change the parameters to see how it will affect your result. First, I will just do fit transform, and then we will check the result. And then I'm going to use supervised UMAP approach to get the result. After we use the supervised UMAP approach, I'm going to put some test data. That means I place some new data points into those clusters and see how it goes. Because I run this program already, I won't run it again now. One reason is it will take a long time, but you can download the source code from my GitHub and try it by yourself. First, let's take a look at our input data. We have 10 digits here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there are 8 times 8 pixels. And first, we'll apply UMAP to our data to transform to three-dimensional digits data. You can see this is our result. And all those digits are separated nicely, but you can see here this is number 6 mixed with one number here is number 5. So our model has some hard time to distinguish this number 5 from number 6. If you check here, it's number 8, and in the meantime you can see some number here. It's number 9. So our model also had some hard time to distinguish number 9 from number 8. Then we are going to use supervised UMAP approach. This is the result. You can see all the numbers are separated nicely because we used supervised UMAP approach. And after that, we are going to give it some new data points and rerun the new map. And you can see this is number 1 and some number 8 mixed in. And this one is number 6. And there's a number 5 mixed in. But in general, we got very decent result. All those numbers separated nicely. This is why and how you can use UMAP to do dimensionality reduction. Please provide your comments and subscribe to my YouTube channel. Thank you for watching.